When NASA retired the Space Shuttle, the agency found itself in a bizarre position. They had no clear, unified, apolitical plan for what to do next with human space exploration. Under the Bush administration, the directive was the Constellation program. The idea was to build heavy-duty hardware to push deep into space. The project proved expensive, fell behind schedule, and ultimately failed to deliver completed hardware to the launch pad. The Obama administration scrapped the moon return entirely. They argued astronauts had already been there and pivoted the agency's focus toward a highly complex asteroid redirect mission. Fast forward to the Trump administration, and the target flipped back to the moon, but with a sudden, politically driven mandate: land humans on the lunar surface by 2024. The engineering reality simply could not support that deadline. Meanwhile, China rapidly advanced its own lunar infrastructure timeline. They are currently on track to establish a physical lunar presence in the 2030s. This geopolitical pressure created a hard deadline that American policymakers couldn't ignore. That pressure catalyzed the Artemis program. Instead of launching isolated missions to plant a flag and take photos, NASA committed to a rigid, step-by-step roadmap designed specifically to build a permanent settlement. Decades of political theater and shifting priorities have been cast aside. International competition forced the United States to commit to a calculated, public-private engineering pipeline with a clear, singular focus. That pipeline begins with Phase 1. Artemis 2 will use the Space Launch System to orbit the Moon, testing the capsule's life support. Artemis 3 introduces the actual hurdle, landing humans back on the surface. Unlike the Apollo days where NASA owned every piece of hardware, this time they are purchasing services from private companies. To prevent a single company's engineering delays from stalling the entire program, NASA intentionally funds competing lander designs. SpaceX is developing a customized lunar version of their massive Starship vehicle to act as one of the primary landing systems. To guarantee redundancy, NASA also brought Blue Origin on board to develop a backup lander. If one vehicle isn't ready by the target date, the other can step in to complete the mission. Getting down safely only finishes Phase 1. Once astronauts arrive, they immediately face Phase 2, navigating an incredibly hostile, cratered terrain. For this, NASA is contracting lunar terrain vehicles. These rovers have to pull double duty. They must handle standard crewed driving while also functioning via remote control from Earth. This allows scientists to explore hazardous slopes and deep craters even when the human crew is fast asleep. They are also developing probe systems called Moonfall drones, or hoppers. Because helicopters won't work in a vacuum, these probes use quick rocket bursts to jump across the airless surface. Their primary job is mapping out exact locations at the lunar poles that receive perpetual sunlight. Redundant landers and jumping probes solve the physical geometry of reaching and moving across the moon. They do not, however, solve the ultimate engineering bottleneck: surviving the darkness. The greatest threat to a permanent base is the Lunar Night. It lasts for roughly 14 Earth days. During that time, temperatures plummet, and standard solar panels are completely useless. To survive a 2-week deep freeze, NASA requires a 3-tier escalating nuclear power architecture. This diagram shows how power output scales up across each level of the base's development. Tier 1 relies on radioisotope heater units. These are tiny, shielded capsules of radioactive material that emit a single watt of energy. They aren't meant to run computers or motors. They exist purely to generate ambient heat, preventing batteries and delicate electronics from cracking in the dark. Tier 2 utilizes radioisotope thermoelectric generators. These systems produce over 100 watts of continuous electrical power. They ensure core life support systems in the habitat and larger rovers stay functional, regardless of whether the sun is shining. Tier 3 introduces Kilopower reactors. These are heavy, sustained baseload generators capable of providing up to 10 kilowatts. That is the massive electrical output required to power an active, permanent human colony. Solar energy will handle the daytime operations, but without fully committing to this specific nuclear hierarchy, continuous human survival on the moon is a physical impossibility. Once those kilopower reactors are active, they serve a specific industrial purpose, running high-powered lasers directly on the lunar surface. The plan is to take the raw lunar regolith, the abrasive dust covering the moon, and use those lasers to melt it down. The molten dirt is cast into solid bricks, which astronauts will then use to construct heavy, radiation-shielded homes. This vision of heavy industrial permanence is a sharp departure from our history. Apollo was a brief sprint, optimized to get a few people safely to the surface for a few days and immediately bring them back. NASA's ultimate metric for the success of Artemis is frequency. By the late 2030s, the goal is to establish a routine schedule where a crew flies to an international lunar base every 6 months, like clockwork. The true triumph of the Artemis program won't be producing a single exciting masterpiece mission. The triumph will be building the infrastructure necessary to make humanity's presence on the moon completely, methodically enduring.